We are next going to look at an example dealing with simulated data so that we know what we would expect to occur, and we would show that indeed that it does occur. So much of these notes here are going to allow us to also see how we can work with this kind of data in R, and how to estimate in the corresponding model, how to forecast with the corresponding model as well. So there are a number of R packages available to estimate these arch models in R. Here are three of them. The Garch package is one that we will primarily focus on. You will see some people look at the T-series package. While I have actually even used that in the past in this corresponding course, it doesn't give as much of it's not as fully functional as the Garch package, and I would always need to start using the Garch package. So in my recent revision of the course, I decided to remove the T-series information. However, I have left information about how to use T-series in my corresponding programs. Now, a little bit even more flexible package than Garch is the Garch package. To some respects, it's a little bit too flexible for what we want to do, and I think it's easier for us to use the Garch package, so that's why I focus on that here. I will show a little bit about how to use Garch later in these notes. Now, if you want to see more information about other kinds of Garch models, other packages that are involved that are available for it, I strongly recommend that you take a look at the Finance Task View for R, which summarizes all the packages out there that are meant for financial data. Ours has a number of task views like this to summarize certain segments of to summarize what R can do for certain segments of the R community, and this particular task view will be useful for Arch and Garch purposes. Okay, so what we're going to do is we're going to generate data from an Arch 1 model where alpha 0 is equal to 0.1, alpha 1 is 0.4. Here's the corresponding code to simulate the data. We're going to approach this from a for loop standpoint, similar to what we've done in the past, like with an AR1 model. So I'm going to set a seed so I can reproduce my results. I'm going to simulate 1,100 different values from this corresponding Arch model. Do note, though, that I will chop off the first 100 and just keep the last 1,000. A is going to be my vector. It's going to be a vector that has alpha 0 and alpha 1 in it. E is going to be essentially the epsilon portion of the model. And I'm going to simulate it from a normal distribution with mean 0, standard deviation of 1. I'm going to save my values of y into a vector, which I'm just going to initialize as numeric length of n. And I need a way to first start this process for what y will be, since y is dependent upon the past with this kind of model. So y1 is going to be simulated from a normal distribution with mean 0, and the standard deviation here, notice that this is alpha 0, here is alpha 1, and where I get that from corresponds to what we saw in a previous set of notes for what the distribution is for y sub t. Then I go into my for loop. I'm going to start from 2 to n, and here's then my corresponding model, y sub I, or I could have called it y sub t. I generally don't use t as an index for loops because t also is a function that corresponds to taking a transpose of a matrix. So y sub I is equal to my epsilon at time period I times the square root of alpha 0 plus alpha 1 times y sub t minus 1 squared. So that's my for loop, and then what I return for my y is the last 1,000 of these values that were simulated, And also just for later, so that I can work with this, sometimes I work with y in other ways. I create an object called save.y to save this data in case I write over y for some other purpose. Okay, so that's how you can simulate the data. Here's a plot then of the corresponding data, and as we've seen in past plots like this of time series, we do have some parts of it where we have a larger amount of variation than we do in other parts of the series. So we have this non-stationary variance, but these are short time periods. Now, while I use y here to represent my data that I'm simulating, in actuality, to some respect, in actuality, we would still need to estimate the mean of the series, and it wouldn't be exactly equal to 0, even though the way the model is set up is for mu to be equal to 0. So in actuality, you can think of the data that I simulated as x of t, and then we would adjust it by the mean, and that would be my y sub t. Okay, so that will be one way to simulate the data. I purposely do that to show you that, how things are coming about through past values. It just is helpful to better understand the model itself. Now, the primary way that we will actually simulate data from a Garch model is to use the Garch sim function that's in the Garch package. In case I didn't say this before, the packages I introduced at the beginning, all of them are packages that you will need to download and install yourself. These are user-contributed packages. So once I do that with fgarch, I can say library fgarch to use functions within the package itself. Then I set a seed so I can reproduce my results. And while I could do this inside of Garch sim, I decided to do it outside of it. I'm going to create an object called spec, which means model specifications. What model am I going to use for this corresponding data? And I use the Garch spec function to do this for me, where I say the model is, and I put together in a list omega, which is our alpha 0, plus alpha, which is our alpha 1. Notice that's that 0.4. If I had also an alpha 2, what I could do is use the C function to combine the different alpha values. And then also I have an argument called beta. If you remember when I actually represented or showed you what the general representation of Arch model is, the Garch model, if you remember there was some beta parameters. And so since I'm not specifying any beta parameters at all, I'm going to set it equal to 0. If I don't do that, this function will use a default for what beta is, and you will actually have one beta parameter contributing to this model that we're actually simulating, or simulating data from. So then I say Garch sim. For my spec argument, I put, well, what did I do for spec? And I want 1,000 different values. I'm going to put an object called x, and here are the first 6 values shown there. Here are the last 6 values as given by tail. Now, something that's quite annoying with this particular function is that it will automatically put dates associated with simulating this data. And so that's why you see those dates there. This Garch here corresponds to our x. So here's x sub 1,000. Okay, so let's do a plot of this data. And this is what we get. So again, we have some extra variability in comparison to other places in the time series. And so that's why an Arch model would be appropriate. Okay. Now, in a typical model building situation, you won't necessarily know going into the data that indeed a Arch model is going to be necessary. So what you would do is do an ACF plot of the x of t's. You do a PACF plot as well. And then if you're starting to suspect that indeed a Garch or an Arch model might be necessary, then you also can do an ACF and PACF plot of xt squared. So let's do that. So first of all, here's my plot for just x of t itself. And again, we ignore lag 0 there. And what we can see is that pretty much all the autocorrelations, all the partial autocorrelations have small values that are non-significant. Yes, we got some that are really borderline here, but in the end, they're not too far past. And notice I'm going up to lag 30 there, so it wouldn't be necessarily unusual to have some that are slightly outside of that plus or minus 1.96 divided by square root of n range. I'm not worried about this. I think I have pretty much what looks to be white noise, except for perhaps the variance aspect. And so let's take a look at then the Acf and Pacf plot of x squared. Now we're seeing some stuff here. Notice at lag 1 for the Pacf, we have a significant value. For the Acf, again, we ignore lag 0. We also have a significant one there and a marginally significant one there. And again, we simulated data from an arch 1. So what that means for us, and drawing in relationships to what we've seen previously with the ARMA models, is that we would expect the PACF to cut off to 0 after lag 1. This is happening here. We would expect the ACF plot then to tail off to 0 as well. And we sort of are having that too. So we have this similar behavior, and this is telling us that indeed an arch 1 model would be appropriate, which matches what we used to simulate the data from. Okay, so let's go ahead and now estimate the model. I'm going to put the results into an object called mod.fit. I'm going to use the Garch fit function from this package to estimate the model. And in the formula argument, this is where I specify the structure of the model. And I need to say tilde, and then essentially I'm using a function called Garch to specify the particular model. The first entry here is my value of m, so m equal 1. And we again briefly talked about Garch models in the past, and we know that there are different beta parameters associated with a Garch model. And so the second value there corresponds to the value of r, which I'm going to set equal to 0 because we're just focusing on arch models right now. My data is in x, and include.mean equal true, meaning that I do want to estimate mu. Okay. And so what that will essentially do then is that our y times t is going to be xt minus mu, whatever, or mu hat, you could say. Now, by default, Garch fit prints a lot of information right after you estimate that model. It gives you information about how the model fitting process is going and so on. And if you don't want to see that, and I've excluded most of it from my output, you can say trace equal false to remove that information. Now, I can summarize my fit by applying the summary function. And this is what I get here. So for example, notice how it says conditional distribution, norm. Remember, yt given y sub t minus 1 is a normal distribution. Here is my mu hat. Here's my alpha hat 0. Here is alpha hat 1. Standard errors are based upon a Hessian matrix. Remember when we talked about the basics of maximum likelihood estimation before, that Hessian matrix plays a role in finding the covariance matrix for the parameter estimates. So that's where that is based upon. So we also then have these parameters stated again. Here are the corresponding standard errors. So here's the square root of the estimated variance of alpha hat 1. Then we have a t-value column. This corresponds to, let's say, calculating a test statistic called z, which is 0.4244 divided by 0.0608. Then if we use a standard normal approximation, even though it says t, if we use a standard normal approximation to this, we get a very small p-value when I'm testing whether or not alpha 1 is equal to 0 or not. So there is sufficient evidence to indicate that alpha 1 does not equal 0. Similar tests are done with the other model parameters too. Some other stuff in the output. So we have a table here corresponding to tests involving residuals. We have what are two commonly used tests for normality for a sample. One's called the Garch test, one's called the Shapiro-Wilk test. Here's their corresponding statistics, p-values here. HO is we have a normal distribution, HA not normal, and the p-values are large, indicating there's not sufficient evidence to indicate any deviation from a normal distribution. Don't worry about the actual formulation of the hypothesis test. For our particular class, it's okay just to go with what the results are. As you might imagine, there's other ways to check for normality too. We will see them later on. You know, use a QQ, apply the residuals, use histogram as well. Then we have some Jung-Box-Pierce test statistics here. We have two separate ones. Notice we have some that are labeled with R. That corresponds to the residuals themselves. And for lag up to lag 10, for the test of all these autocorrelations, we get a p-value that's relatively large. So there's not sufficient evidence to indicate evidence against non-zero autocorrelation. We also see an R squared there for lag 10, 15, and 20. This corresponds now doing the same test for the residual squared. Remember in the past how we looked at x of t squared to better understand our time series there. And we looked at the Acf and Pacf plots. Well, this is now doing the Jung-Box-Pierce test with these now the squared residuals. And what it appears is that the Arch-1 model is correctly accounting for the dependent structure amongst the xt squares because the p-values are all large there. So this is a good sign, and this is what we would expect with an Arch-1 model. Or when we know that we simulated data from an Arch-1 model. I guess in other situations when you don't know how the data is simulated, you wouldn't necessarily expect that. Okay, so some notes here. So when we specified the model in Garch fit, what came first was M, what came second was R. This is not always consistent, the ordering that is. It's not always consistent in all R packages or even software outside of R. So you've got to be very careful. You need to know the ordering of M and R whenever you're working with these kinds of models. We talked about trace equal false. Now, when running this code to prepare for, or in the latest revision of my notes here, I was getting this particular message, which I excluded from the output. And what I believe this message is corresponding to, this warning message, is that there is some code inside of the Garch fit function that needs to be updated to new standards in R. I reran this code using, doing model fitting with this data with other packages, and I get the same model as I do in this with using this package. So I don't think that this is anything to be worried about. This all matches what I had previously in previous times I taught this course, and so I think everything is okay here. I think it's just a matter of the authors, someone telling them that, hey, this warning message is now appearing, and then the authors will put together a revised version of the package that corresponds to the new standards of R. So then the warning message is not printed. Okay, so here's our data. Here's our model. So remember, mu hat is 0.0004 based upon what was in the output. And we're just simply saying x of t is equal to mu hat plus wt. That's our model where wt is distributed normal, means 0, variance sigma hat squared sub t, where the sigma hat squared sub t is equal to alpha 0 plus alpha hat 0, plus alpha hat 1, y sub t minus 1 squared. You can think of this as our residual, because notice x of t is equal to mu plus wt. In other words, x of t minus mu is equal to wt. So y sub t is equal to xt minus then the estimated mean. Equivalently, in this kind of a simple setting, since this is essentially, you could say, our ARMA 00 model, we could also just simply state the model like this. Y sub t, our mean adjusted version of x of t, as sigma hat t times epsilon sub t, where here's my sigma hat t squared once again. Y sub t is x of t minus mu hat, and we say that epsilon sub t is distributed independent. So I should have had independent here. Independent, normal with mean 0, variance 1. Okay. Now look how close these parameter estimates are to what we used to simulate the data. Alpha 0 was 0.1, alpha 1 was 0.4. And if you take into account the standard errors, in fact, you could even do a confidence interval for alpha 0 and alpha 1, and you're going to see that the true value of alpha 0 and true value of alpha 1 is inside the intervals. And this, again, just to emphasize this is why we, in a teaching situation, is very useful to start from a perspective of, here's some simulated data where we know what's going to happen. Let's see if it does when we apply it. And as long as it does, hey, everything's great. If it doesn't, then it might be thinking, okay, maybe you don't understand the model as well as you should. Maybe you're not writing the R code correctly, and so on. Okay. So we talked about this bullet in terms of how to do the test. We talked about the junk box pierce. We talked about the test for normality as well. Now, with our original simulated data, where I simulated with a for loop, one could estimate the net corresponding model. You should try that on your own. Actually, the code is in the program, so you could run that, and we get what we expect. Again, alpha 0 was 0.1, alpha 1 was 0.4, and we're getting, generally what we would expect. Okay. Now let's look at how we can extract some information that's stored in mod.fit. Mod.fit is a list similar to what we've seen previously with other model fitting functions. But there's something different here than what we've seen in the past. And that is, if I want to see what's inside my list that's returned, normally I would do the names function with it, like names mod.fit. In this particular case, I cannot do that. It's not going to work out. In fact, here it is. It doesn't work out. Instead, I have to use a function called slot names. And then it's going to behave like what I would normally expect with names. Well, why does this occur? Well, the R language itself was originally based upon a version of the S programming language. The S programming language came about in the 1970s from AT&T's Bell Labs. Actually, I think it was just called Bell Laboratories at the time, excuse me. And R is based upon a version of the S language called S version 3, or people just often say S3. Almost all of R is still based upon that language syntax. It's not exactly S3, but it's based upon the same ideas that were introduced then. Since R originally came out, there have been other versions of S released. There's been even other syntax ways of using R that have been released as well. None of them have really caught on to a large degree. Probably the one that caught on the most was something called S version 4, especially in the early 2000s. And this particular package here, F-Garch, was written using the syntax associated with S version 4 that's built into R as well. And so the main thing that is really important for us with understanding S version 4 type of syntax is that in a list for S version 3, it has components. You access parts of the list using a $ syntax like mod.fit $residuals. Now with S version 4 though, you replace the $ with an @ symbol. So mod.fit at residuals gives you back your residuals. Because of this different version form, some basic functions like names was replaced with slot names. And sorry, I should also mention that the stuff that's after @ is no longer called a component. It's now called a slot. Okay, so it's really not too difficult to do them, to use S version 4. I guess my number one frustration sometimes with this is that sometimes package authors are not consistent in what they do, and they actually mix S version 3 with S version 4 within inside the same package, and that's very frustrating then to try to extract things from an object, because you don't always know, at least immediately, well, is this an S version 3 or is this S version 4? So anyway, enough about that. So if I'd say slot names here with mod.fit, I get information about, well, what's stored inside there. So for example, if I wanted the predicted values for x of t, I can pull out the fitted slot of mod.fit. Here are the last 6 of these estimated values from the tail function. If I want to pull out the residuals, I do at residuals, and here we go. And just to show you how these residuals are calculated, suppose I take x minus those fitted values. What do I get here? It's those residuals. Okay. Now take a look at these fitted values though. They all should look familiar. They're mu hat. Well, why? Why are all these predicted values equal to mu hat? Well, remember what our model is. X of t is equal to mu plus WT. WT, of course, has a mean of 0. So what's all the predicted values? In fact, what's all the forecasted values for this particular time series? Simply mu. Now, there is also a function R called residuals, which will allow you to extract those residuals as well, so you don't have to use the slot name to do it. These kinds of functions, in case I haven't ever said this before, are often called accessor functions, A-C-C-E-S-S-O-R. Also, some other things that we could get as well. Here is sigma hat t as estimated from the corresponding model. Just to show you how this is calculated. Excuse me. Remember our model structure. If I were a sigma hat t, or sigma hat squared would be equal to alpha hat 0 plus alpha hat 1 times y sub t minus 1. Remember, I have 1,000 observations. Y sub t minus 1 is x sub t minus 1 minus mu hat. Then we square it. If I just want sigma hat t itself, then I take the square root. And so if we notice here, that last value is 0.314, which is what we can extract out of that object. Some other things here. If you want to see then the corresponding parameters estimated that are stored inside the object, you can do mat coef to pull them out. So if I did mat coef, mat stands for matrix, coef stands for coefficients. If I did the 1, 1 element, here is my mu hat. And I could find my regular old residuals by taking x minus mu hat remember the formulation of the model, divided by what that sigma hat sub t would be. There's my residuals. And this is what I get right there. These particular residuals, those are different, and I should have brought this up to begin with. These are different than the ones that we had before. These residuals now are for the arch model part itself. Now again, we could write our arch model like this. So we could then equivalently write this as epsilon is equal to y sub t divided by sigma sub t. And what this code here is doing is essentially finding the residuals from the arch model in this manner. So the epsilon is our error term, and we could try to estimate that. That would be then like a residual. And so if I then put a hat on top of the sigma t, that's where that is coming from. Y sub t, of course, is x minus mu, or in this case now mu hat. And so here are those residuals now from the arch model itself. And I can also extract those by saying residuals mod.fit. And if I say standard I is equal true, this is going to also get those residuals. Okay. Now let's do an Acf and Pacf plot of the residuals, similar to how we've done these kinds of plots before for a regular ARIMA model. So if I look at the Acf and Pacf plot of these particular kinds of residuals, this is what I get. Notice no significant values. Of course, ignore the lag 0 part there. And so what this is telling me is that this particular model is doing well. Okay, some notes. We've talked about these. We talked about that. This model is working well. Now, the authors of this particular function have set up a method plot function to work with the generic plot function to do some typical plots that one would like to do. And so if I say plot, then with mod.fit, what happens is in my R console window, I have all this information printed, and what this is saying is that I can choose among 13 different plots to examine my model further, examine my data further. And so this will be blank, and then you just simply type whatever number for a plot that you want. If I type 1, I get the plot to my regular old time series. So it's essentially the same plot that we started off with at the very beginning. Now, also, I could type, let's say 5 for ACF of the squared observations. Remember us looking at that before we even estimated the model itself. And what did we see? Well, we saw that tailing off towards 0 there. I could do an ACF of the standardized residuals. This would be plot number 10. This is what we get. An ACF plot of the standardized residuals squared as well. This is what we get, suggesting that no further changes need to be made, or no changes need to be made to our arch part of our model. And again, many plots. Here's a QQ plot, and as you expect, since we started with a normal distribution to begin with, the QQ plot looks really good. The points are very close to that line. Now, there are ways too that you can specify just getting one plot at a time. So if I say plot and then add the argument which, that allows me to immediately go to a particular plot number. Of course, you need to know what the plot numbers correspond to beforehand. Okay. Well, what about forecasting now for our overall model? So this is forecasting for this model, which then takes into account that WT, distributed normal, sigma squared t, and sigma squared t. Oops, no, I'm running out of room. Sigma squared t is then based upon our alpha and y sub t minus 1 squared. Okay, how do we do forecasts? Well, we can use the predict function to do these forecasts. We put in information about our model's fit. How many time periods ahead do I want to go? Let's say I want to go 1, 2, and 3. Let's say I want a plot of the corresponding forecasts. On this plot, I can specify the number of actual time points for the observations themselves to plot. So nx equal 3 means, okay, plot information about time 1000, 999, and 998 in terms of showing that on the plot. If I don't do that, the whole time series gets plotted plus the forecast. And since I have 1,000 observations, that would make the plot very difficult to read. Then with my forecast, say I want 95% intervals. So this is what we get. So here's our forecasted values. They're all equal to mu hat. And using the notation that we've seen before, x tilde sub n plus m, n is the 1,000, m will be 1, 2, or 3 in this case, and be careful, this m actually means number of time points ahead, not the order of the arch model, excuse me. N would be 1,000 there as well. This is what we would get. Here's the corresponding confidence interval. So negative 1.08 about is less than x sub n plus 1, or let's just put 1001, is less than let's see, 0. Oops. It's less than 1.07959 and so on. So that's our first forecasted value for x. How is this calculated? Well, first of all, let's take a look at the plot. And so what we can see here, so this is actually time point 1000. This is time point 1001. We can see the confidence interval bands there as well. I'm not really for sure why, but the authors say, well, we need to make sure that people understand that this is the upper band, so we're going to make that a blue value, and we're going to make the lower one a green value, and we have all these weird light blue lines drawn up and down there. That's a lot of busy stuff there. Here's then the corresponding forecasted value. Notice how that's constant for those 3 different time points, because remember it was just mu hat. Okay, now how are these forecasts found? Well, so our model starts with this, or our data starts with this x of t. There are no regular moving average or autoregressive parameters associated with this model. We will take a look at an example later that does look at those kinds of models and see how to approach that. But for now, we have a very simple situation where essentially we have an ARMA 0-0 model. So because of that, then the forecasted values are all mu. We also set that what that means is that y sub t then is equal to x of t minus mu. So it's this mean adjusted value. You can also kind of think of it as y sub t essentially as a residual. We could find forecasted values here as well for those y sub t's. Those are all equal to 0. So as I said, the forecasted value for x sub n plus m is this mu hat. And so what we need now is to figure out, well, what would the confidence interval look like? So we need a variance. So we need, similar to what we've done before, we need this variance of the forecast error. Now, because of the simplicity of this model, this then is equivalent then just to simply the variance of y sub n plus m minus that corresponding forecasted value. So if we plug in what this is, we're left with just that sigma times the epsilon. And again, this m has nothing to do with the order of the arch model. It's just, unfortunately, redundant notation where, in the past when we did the forecasting section, the m always corresponded to number of time points ahead. And so, well, what is then this corresponding variance? Well, this epsilon, remember, has a variance of 1. If I factor out that sigma, then I get sigma squared n plus m. Okay. So then, also, we know how these sigma squares come about through our arch model. Since these sigma squares come about on our arch from our arch model, sigma squared sub n plus 1 time point ahead, is just simply alpha 0 plus alpha 1 times y sub n minus 1 squared. So let's substitute parameter estimates. Substitute n equal 1000. Let's do the calculation. Here's alpha hat 0 plus alpha hat 1 plus, this is x 1000. Here is mu hat. Now remember, y 1000 would be equal to x 1000. If I can write it out, minus mu hat. Then I square it, and then I get a value of 0.303. So what this is telling me then is this variance here, when m is equal to 1, I estimate it with 0.303. Let's go back to our output that we saw previously. Okay. If I were to take the square root of that 0.303, I get 0.550629. So we can see that standard deviation then is actually represented in the corresponding output. Okay. So then my confidence interval, my general, let's say 1 minus alpha times 100%, where alpha means then the corresponding corresponds to our confidence level. Then the 1 minus alpha times 100% confidence interval for x of n plus 1 is just the forecasted value plus that value from this standard normal distribution times the square root of the estimated variance. Okay, so let's go ahead and figure these values out. So here is then that predicted value or forecasted value, which again would be mu hat. Here's the value from the standard normal distribution. And then here is my sigma hat sub 1001. Here's how I figure it out through the means that we previously saw. And here's my confidence interval, which is exactly as what was given in the output. So through using these simple by hand calculations, it's reassuring then that we're getting what the output gives you, and it gives you some information about how are those calculations being done. So what will we do for 2 time points into the future? Well, we essentially would go about the process just like what we just did here. Now take into account what we got for time point 1001. I will let you go through the details here on your own. Again, the key is my by hand calculations match what was in the output. Okay, let's now talk about the Garch package, just briefly, so that you get an idea of how to work with that package. As I mentioned before, the Garch package allows you to have a little bit more flexibility. It makes it maybe a little bit more difficult to use in the end, though. Also allows you to explore a number of different models that fgarch does not. Most of these models, though, we wouldn't have time to get to in our particular course, though. So that's another reason why I focus on fgarch. So to work with this this package, I wanted to estimate a model to my original data that I actually estimated, that actually generated from my for loop. So to estimate our model of interest, I put Garch fit. I specify my data, and then also I have specifications corresponding to the model, which I had created right up here. So to specify our particular kind of model, I would say Garch spec. I say, well, what is the model for my variance? And inside the list, I need to say model equal sgarch. That's just their way of saying it's like our kind of model, like a standard Garch model. Garch order, here is M, here is R, the same order of the M and R as we saw previously with fgarch. And then also I say, well, what do I want to use for like my regular old ARMA model? And that's what the mean.model argument stands for. And so I can say list armor order, P is equal to 0, Q is equal to 0. Make sure you estimate the mean. And while this is the default, I wanted to mention this. Notice it also allows you to work with RFEMA models. Now, depending upon the semester that I teach this, sometimes I will talk about these additional types of models called RFEMA models. If so, if this was this particular semester, then you probably think this is kind of cool right now. If, however, this is a semester where I did not talk about RFEMA models, then don't worry about it. But my notes and my videos for RFEMA models are available online. You can always look at those if you want to learn more about this other kind of type of time series model. Okay, so I put the results into mod.fit. And then when I say summary of mod.fit, I don't get much back. Unlike what we got previously from the Garch package. Now, for S version 4, which is actually, this package is written using S version 4. Typically, except for with the Garch package, the summary function doesn't do the same thing as we've seen previously. Rather, instead, the summary function is usually replaced with the function called show. So show mod.fit, show what's inside of it. And this is what we get. So we get mu hat, we get alpha hat 0. Here is alpha hat 1 as well. Again, this is for the original for loop data that I had simulated, not the data that I ended up primarily focusing on when we were using Garch. So we get a lot of other good things listed in the output as well. You can take a look at that on your own if you're interested. Here's simply where the model is stated as well. If I wanted to simulate new data in this package, I can start actually with a model fit, like what we just got done doing, and simulate data from using that alpha hat 0, that alpha hat 1 that's inside of that model fitting object. And so I can set a seed to reproduce my results, and I can use a function called uGarchSim, where I put fit equal mod.fit. How many observations do I want? Let's say 1,000. It returns an S4 version object. And so if I say slot names, I get information about what's returned to me. And to actually see the simulated series itself, I can pull out of the data that I simulated, and that actually should have been X there, excuse me. I can pull out the data information about the data that was simulated by saying simulation, and notice how it's actually combining both S version 3 and S version 4 type of object, which is not good. But anyway, there's where the simulated data is. So that just gives you a really brief introduction to what this particular package can do. And then that concludes then this simulated data example dealing with an Arch 1 model.